Okay, these are the 7.6 notes, rational inequalities. We'll see if we can get through the first couple of pages and then do all the examples in a separate recording. So we are going to take a look at this conceptually. We're definitely not going to just graph and say, hey, here's where it's above the x-axis and here's where it's below. So we've got to have some foundational and fundamental understandings. So let's start with the warm-up here. If I am going to subtract rational expressions, we got to have a common denominator, same as with numbers. So here's the thing. I cannot make this denominator the same as the first one by just subtracting 4. We know that we cannot add and subtract to the numerator and denominator and make an equivalent fraction. So here, because we don't know what x is, we don't know what the relationship is, we are going to go ahead and multiply both parts by the other denominator. So I get 7x over x times x minus 4, and I am going to suggest that you keep things factored, because if at the end we can go ahead and subtract something, or cancel something, we're going to need to factor the denominator anyway. So I have a common denominator of x times x minus 4. In my numerator, I've got 7x minus 3x. Then I also have minus negative 12, so that ends up being plus 12. I get 4x plus 12 over x times x minus 4. And if I want to be really picky, I can go ahead and factor the 4 out of the top. I'm not going to have anything that can cancel, but I'm going to leave my answer like this in factored form. B is a little different. We don't have an expression, we have an equation. My x is in the denominator, so I've got to start by getting it out of the denominator. I'm going to multiply both sides by x minus 4. Keep in mind, this is different than what we did in the expression. In the expression, we multiplied both numerator and denominator by the same thing, so we could get a common denominator. Here, my goal is to cancel that denominator. So now I have 7 equals 3x minus 12. I'm going to add 12. I get 3x equals 19. And x equals 19 thirds. I'm not going to worry about converting that to a mixed number. Keep in mind that there is an issue here. Because of this denominator, I know that x cannot be 4. That would give me a 0 in the denominator. But that's not what we get as an answer, so we're good. So now we want to solve rational inequalities. Up above, we had a rational equation. We are going to solve roughly the same way, but there are other things that we have to consider in our answers. So the first thing I want to point out is we know what happens if we solve and we get an answer like this, x equals 3. And we don't do this very often anymore, but that would mean I would plot a point on my number line right there, showing that x equals 3. Okay. Suppose, though, that we get the result that x is greater than 3. Strictly greater than 3 means we cannot use 3. A lot of times you'll see that with an open circle. I want all the values greater than 3. 4, 5, 6. Sometimes it helps if you're unsure. Go ahead and plug in a number and test it. Okay. So now we are looking at solutions that involve more than just a single answer. So for those of you that like steps, we have some steps here. To solve a rational inequality, first thing we want to do is make sure everything is on one side and you have a 0 on the other side. Now, it's a rational inequality. You cannot multiply both sides by the denominator when you have 0 on one side, because that eliminates anything that the denominator has to offer. Okay. We are going to determine where critical points are, and we're going to talk about those here in just a minute. We're going to use the critical points to divide the number line into intervals. Okay. Our critical points are going to happen where our expression is 0. We know that the only way our expression can change from a positive answer to a negative is if it crosses 0. That's why 0 is important. The other place that we're going to worry about is where our expression is undefined. Because if it's undefined, we probably have an asymptote right there, which means our rational function could look different on one side than the other. Could have positive y's on one side, negative on the other. Could be positive on both sides. We don't know. We'll check that. Okay. We are going to evaluate the factors in the numerator and denominator, and then we will decide whether values in those intervals are positive or negative. And we're going to go through all that in just a minute here. And then we're going to make sure we write the solution in interval notation. Okay. So take a look at our first example. X minus 1 divided by x plus 3 is greater than or equal to 0. Greater than or equal to 0, that means we are looking for where our values are non-negative. They're either 0 or positive. Okay. We have got the numerator. If the numerator equals 0, this makes our value, our y, let's do it that way. So anything that makes the numerator 0, doesn't even matter what's going on in the denominator, really, means that our y equals 0. Okay. Anything that makes the denominator 0 means we cannot use that value and we've got an asymptote. Okay. These are the two places that our function can change values. And that's why we're calling those our critical points. Okay. Oops. X, back up. Nobody corrected me here. Erase, erase. I can't always talk and think at the same time. X equals 1. Okay. So notice here we've divided our number line, our real numbers, into 3 intervals. And it doesn't really matter here that we distinguish where our asymptotes are, where our zeros are, just that we know that's how we're dividing our intervals. Okay. So I've got 3 intervals. I've got negative infinity to negative 3. I've got negative 3 to positive 1. And I've got 1 to infinity. Now, our function cannot change sign anywhere else. Either it goes through a 0 or there's an asymptote. So there's no chance in any of these given intervals that my outputs are going to have different signs. Which means if I pick a number and I end up with a positive answer, all of the values within that interval are also going to have positive answers. Okay, so here's what we got. Over here in our left-hand interval, we're going to pick a number that we can plug in. And the example here uses negative 4. We plug in -4 for x, we get -4 minus 1, which is -5, -4 plus 3, which is -1, we get a positive value. So I know that everything in this interval, any of the x's that I'm going to plug in, that I am going to plug in, are going to result in a positive y. Okay? We can take a look at our next interval. This one, -3 to 1. Easiest thing to plug in is 0. That's what we do. 0 minus 1 is -1. 0 plus 3 is +3. -1 divided by 3 is going to be a negative number. You will notice when I go through some of the examples, I don't really worry about what the numerator and denominator actually is. I just kind of look at whether it's positive divided by positive, positive divided by negative, figure out what's going on there. Okay. Last interval we're going to check. See if we can get a different color here, because that's what matters, right? Is this one 1 to infinity? So we pick 2. We don't have to get elaborate. 2 minus 1 is 1. 2 plus 3 is 5. I get a positive value here. Now, a couple things I want to point out. We know that x cannot equal -3. That's where our asymptote is. We also know x can equal 1. Asymptote 0. So as we look to solve our inequality, we want all of the values that give us a y that is greater than or equal to 0. Everything over here is positive, right? So we get -infinity to -3, not including -3. That's where our asymptote is. And then we get everything over here, but this time we can include that endpoint, because it's okay to have x equals 1. That just gives us a 0. So we have a square bracket on the 1. And we go all the way up to infinity. And there's our solution. Second example. And the only reason I'm making this recording longer and going through this second example is because it's in the middle of the page. We'll stop here. We'll go page 1 and half of page 2. We will do the next example in the next recording.